d block elements, and I told you that the elements in which the last electron, or we call it differentiating electron. What is the meaning of differentiating electron? Means the electron which differs to elements. The last electron or differentiating electron goes to the penultimate d orbitals are called d block elements. And we know the d orbital can accommodate 10 electrons. Initially, it goes singly to the 5 d orbitals, dxy, dyz, dzx, dx square minus y square, and dz square. After half filled, then it goes for pairing. So 5 plus 5 is 10. When we find that d block elements consist of 10 groups. It starts from group 3 and ends with group 12. That is, it lies between the highly metallic S block elements and non-metallic P block elements. This is also known as transition elements. I've told you the definition of transition element is there, but initially the name was not given like this. The name was given that it is a stage where the metallic property of the elements decreases horizontally to the non-metallic properties. So it is a transition, it is a journey. Okay, but later on the definition is being changed, mentioning that the elements in which either in their atomic state or in any of their ion or oxidation state, if they have any unpaired electron or electrons in their d orbital, then we are going to call them as d block elements. Sorry, transition elements. So that way, in group 12, all the d orbitals are paired up. And s orbital is also paired up. So they do not have any unpaired electron in their elemental state or atomic state. These elements are zinc, cadmium, mercury, and the last one is called copernicium. And incidentally, whatever the ions they form, they are all dipositive ion, where you find the electrons only from the s orbital goes out. So their configuration is ns0, n minus 1, d10. So they do not have any unpaired electron. So even though they belong to d block, they are not considered as transition elements. But interestingly, copper and silver and gold, you know that due to stability, copper has an atomic number of 29. So theoretically, it's supposed to have 4s2 3d9 configuration, but that we have already learned in our class 11 is actual electronic configuration is 4s1 3d10. So in that case, copper also should not be considered as transition elements. But copper forms two ions, copper plus 1, we call it cuprous, and copper plus 2, we call it cupric. So cuprous ion has a configuration of 4s0 3d10. So all are paired. But the cupric has a configuration of 4s0 3d9. That is, it has one unpaired electron in its d orbital. Gold shows two oxidation states, +1 and +3. Gold 1 is 3D10, but +3 has D8 configuration. So it has two unpaired electrons. So they are being considered as transition elements. Okay. Then after that, we have discussed about when we started discussing about different physical properties in the form of atomic radii and ionic radii, we have found a very unique thing. Generally, atomic and ionic radii steadily decreases when you move from left to right. In case of transition elements also it occurs. But after moving after few elements, we find whether they're atomic radii or ionic radii, they show almost same atomic radii. And almost at the last, with group 11 and 12, the atomic radii again increases. This is a very unique thing. Then a proper explanation is being given. We have many things we have told in theory there. And later on, when we started verifying from their experiments, we found all our theories are correct. We have not seen any orbital. Mathematically assume that S should be spherical, P should be dumbbell shaped, D is double dumbbell shaped. And we also have mentioned the sizes increases from S, P, D, and F. So if it is so, when you put electron in a D orbital, that electron never lies close to the nucleus as it happens in case of S orbital. So every electron does not neutralize the proton which has already entered. And this gradually build up a positive charge. Okay. And in order to mitigate or neutralize that positive charge, nucleus frantically pull all the orbitals nearby. By that way, the atomic radius starts decreasing. And that phenomenon is called improper screening effect or shielding effect. This you have seen in your house also. Suppose your mother is looking for you and she could not find you at home. Then gradually you'll find he is getting more and more annoyed. And when it goes to the intolerance level, then she started shouting. Moment you heard that your mother is shouting, you come rushing home. Like that. But side by side, when you cross the half of the mark, we know D1, D2, D3, D4, D5, they're all unpaired. But the moment you go to D6, first pairing starts. When the pairing of electrons starts, the volume of the orbital increases. That you can have an idea. Whatever amount of air you put inside a balloon, if you put double amount, what will happen? Size of the balloon will be almost double. So electrons are like cloud. So as the sizes of the d orbital starts increasing, then the repulsion occurs. To avoid the repulsions, then the orbitals try to move apart from each other. So that leads to the increase in the volume of the atomic orbitals. So two forces are operating. One is the attraction by the nucleus. Second, inter-electronic repulsion. We call it electron pair repulsion. And these opposite forces, when it starts bringing an equilibrium in this process, you find they show an almost stability in their atomic radius. It's almost like a tug of war. If both sides have exact same force, then the rope does not move. But ultimately you'll find one party wins. So just like that, when you go to D9, copper, and when you go to D10, zinc or mercury or cadmium, but when it has all 5 d orbitals filled, expansion takes place and that leads to increase. So please remember. This unique property of atomic radius has made the transition elements or d block elements extremely reactive for different purposes, which we are going to discuss subsequently. Why I am again repeating it? Because P block you might have read a little bit in class 11, you might have forgotten also, but everything we do not forget everything. We have a feeling, or maximum it happens before your exam, that you say, sir, whatever I read, I forgot. No, actually, you don't forget. Only thing is that information is passed to the dormant side of the brain, subconscious side of the brain. Okay? But if you put a pressure, then the window opens and then the information flow. But D block elements you never read earlier. Because of that, again, I am summarizing. Now, we find the D block elements, all the elements in the D block are metallic. That I'm going to discuss later. Metallic property. But as they are metals, they are very hard. And if they are hard, their melting point and boiling point also should be high. Now the question is why they are hard? Why? Sodium is a soft metal, yeah. Even with the help of your nail also, you can tear sodium. Then why D block elements are so hard? In class 11, I told you that we have 3 types of bonding. One you call it the ionic bonding. In fact, it's not a bonding, it is a question of adjustment of charges. Second one, we call it covalent bonding. And third one, we call it metal bonding. So metal-metal bondings are a bit different from the normal covalent bonding which exists in covalent bonds. Okay? But the concept is same. If the bond has to form, there must have unpaired electrons. So if you start from group 3, then it has 1 unpaired electron in d orbitals. Go to group 4, configuration is D2, 2 unpaired electron. Go to group 5, it has 3 unpaired electron. Then go to group 6, it has 4 unpaired electron. If you go to group 7, it has 5 unpaired electrons. But we find that some exception is there. When you go to chromium, chromium is group 6. Okay, in that case we find to maintain stability, it has a configuration of 4s1 3d5. So it has 6 unpaired electrons. So the 6 unpaired electrons, all of them they overlap like this and makes a very strong bonding. Okay, so transition metals are very hard and their melting point and boiling point is also very high because they are the magnitude or strength of metal-metal bonding increases with increase in unpaired electron. Then gradually decreases because the pairing of electrons starts. So when we have discussed about the melting point and boiling point, we find it started increasing steadily from group 3 up to group 6. I have only in the graph I have given you only one series, 3D series. Dear, I told you, please consult the book. Okay. So in that case, we find scandium, then vanadium is more than scandium, then the titanium is more than scandium, vanadium is more than titanium, chromium has the highest melting point. Why? Chromium has the strongest metal-metal bonding due to the presence of 5 unpaired electrons in d orbitals and 1 unpaired electron in s orbital. Then suddenly there is a drop of melting point for manganese. And if you go to the 4D series is technetium. Again it rises for iron, then it steadily decreases. Zinc has the least melting point. You can melt zinc even in your on your LPG stove. Forget about LPG stove. Kerosene stove also you can melt. Why? Being zinc does not have any unpaired electron. And moreover, yes, zinc does not have an unpaired electron. And due to that, you'll find the zinc has the weakest metal-metal bonding. Okay? So in that case, even if you slightly heat it, the metal separates. And very interesting there. If you go down the group that we have learned from our P block, when you go down the group, sizes increases. So cadmium is softer than zinc. And you know that mercury is liquid. Why mercury is liquid? If the question comes, you can't say it is not given in your book. No, you should have that much sense. First of all, they have completely filled d orbitals. So they do not have any strong metal-metal bonding. Moreover, the size of the mercury is very large. So their internuclear distance is also very large. If the distance is large, even the van der Waals force of attraction is also very less. Okay, so that makes mercury liquid. See, everything you cannot read from the book. I have given maximum importance to your theory and conception. That if you know the theory, you can interpret anything. And I told you, where there is a p block elements and d block elements, try to remember only of their atomic or ionic radii. Because everything is being controlled by the atomic and ionic radii. Whether it is ionization enthalpy, electron gain enthalpy, electronegativity, metallic property, everything depends upon that. Thermal stability, I told. Okay. So mercury is liquid because of their first reason is they do not have an unpaired electron to go for effective metal-metal bonding, and due to the larger size, their internuclear distance is large, so their van der Waals force of attraction is minimum. Okay. So now after that, I told you is enthalpy of atomization. Obviously, enthalpy of atomization of the elements also will increase gradually and then it will decrease. Because to convert a metal into vapor, I told you in case of metal, you do not mention the word vaporization. This I can use it only for non-metals. Okay, non-metals, when it exists in the form of molecule. If you hit carbon, it goes to the vapor state in the form of C2. If you hit sulfur, it goes to the vapor state in the form of S2. They exist in molecules, and we are using the word vaporization for that. For in case of metal, it will go in the form of atoms. So we'll call it enthalpy of atomization. So enthalpy of atomization depends upon their melting and boiling points. As the melting and boiling point will increase, their enthalpy atomization also will increase. So we can apply the same concept of atomic and ionic radiation. we can, sorry, melting point concept on enthalpy of ionization. Then why again I have given the summary here? Now I'm going to discuss about the ionization enthalpy. Okay. I think it is property of 5. If I am wrong, you can correct it. I'm going to explain today. I'm not going to write. Ionization enthalpy. First of all, what we can say that ionization enthalpy of the D block elements is more than S block elements and less than P block elements. Why? Because when you have studied the periodic table, did you not mention that ionization enthalpy increases from left to right? So D block elements, see, 1 and 2, S block, 3 to 12, D block, and 13 to 18 is P block. So ionization enthalpy increase from left to right. So obviously this will be this one will be higher than this, and it will be lower than this. Okay, so this is the first one. Now when we move within this group, within this series, we can say that ionization enthalpy increases from left to right. Why? Because ionization enthalpy is being controlled by their atomic radius. If the atomic radius is smaller, distance of the valential electron from the nucleus is also decreases. So the attraction increases. So in this case, you'll find the ionization enthalpy is going to increase. But in many cases, we found that atomic radius is almost same DR. Then you can argue that, sir, in that case, the ionization enthalpy should be same. Yes, I agree with you. But does it not depend upon the effective nuclear charge? We have found that chromium, manganese, iron, cobalt, they have almost same atomic radius of 117 picometer, 117 picometer. But I will find that ionization enthalpy increases. Why? Even if their atomic radii is same DR, but the number of protons inside the nucleus are not same. So obviously attraction is more when more proton is there. So it is going to increase from left to right. Please remember. Okay? Ionization enthalpy of zinc is highest. Because of that, you will find zinc is used for soldering purpose. Why? Why I given this example? The reason is there. Zinc has two advantages. Soldering, because it is soft. Second, as this ionization enthalpy is very high, in that case, zinc will not react with other with the oxygen of the atmosphere as fast as possible. See, zinc coating is being given to our CGI sheet to make galvanized articles because of high ionization enthalpy. Okay. Now, when you go down the group here, when I go down the group 3D series, 4D series, 5D series, and 6D series. In case of P block elements, we have found that ionization enthalpy decreases down the group. But it's very interesting for the transition elements. When you go down the group, ionization enthalpy does not decrease, it increase. So it does not decrease, but it increases. Okay? This one I'm going to tell you when I'll go to inner transition elements. Why the atomic radii? When you go down the group, actually atomic radii should increase down the group, but we find the atomic radii of the 4D series, means second series, is more than that of 3D. But when you go to 5D, 5 atomic radii of 5D is found to be almost same or smaller than that of the series above. Okay, so that one we'll discuss when we go to the inner transition elements or F block elements. A very important factor is there. We call it lengthened contraction or actinide contraction. I do not know, maybe some of your school you have finished D and F block elements, so you will be knowing it. But it will be injustice if I discuss it now because I cannot spend more time on it now. Excuse me. Ionization enthalpy, when it decreases down the group, then it does not show a regular trend. Now see, ionization enthalpy we depends upon that how many electron it loses. Transition metals have 5 unpaired electrons. So one after another electron may go. Okay. So we cannot restrict ourselves only discussion of the first ionization enthalpy. We cannot restrict because we have to take into consideration the second ionization enthalpy, third ionization enthalpy. So transition elements do not show a regular trend in their ionization enthalpy. It depends upon the stability of the ions. If the ions formed is found to be more stable, in that case ionization enthalpy requirement will be less. And if the stability of the ion form is less, in that case you have to employ a lot of energy to remove that electron. See, everything in the universe, whether it's being done by us or by the nature, always moves towards stability. If the future state is not stable, it is not going to occur spontaneously. So in that case, you have to exert force. So whatever I talked about, that increase and decrease, is only about the first ionization enthalpy. Second and third ionization enthalpy of the transition elements is unpredictable. Theoretically, you can predict because if you go for more and more knowledge about it, I cannot involve you in such a tough discussion. But only I can tell you, it shows an irregular trend and entirely depends upon the stability of the future ions. That I'm going to discuss with you briefly when I'll discuss about their oxidation states. So see, when you talk about their ionization enthalpy, in that case, ionization enthalpy means loss of electron. And loss of electron means what? Oxidation. And in electrochemistry, you have already discussed. The amount of energy required, we express them in their reduction potential. Okay? So it depends upon the reduction potential. So we'll find that reduction potential of the transition elements, again it does not show any common trend. Either it may be more or it may be less. Again, it depends upon the stability of their oxidation states. See, I have this note I'm going to send to you. I don't know. I have already in my mobile. I have stored it for a long time, so I'm not able to open it. I think again I have to get it from now. All right. I have specifically written about it. I'll send you. হ্যাঁ আমার পেজটা তো চেঞ্জ হয়েছে দেখতে আসবে পরে এরিয়া কয়জনে ভরে আমাকে দিয়ে দেন so the thing which I'm going to talk to you today is the oxidation state. Transient element shows variety of oxidation states. Variety of oxidation states. And transient element shows the highest oxidation state among all the elements that are in periodic table. I'm going to now write it only for the first series, the 3D series. And in 3D series, transient elements achieve the highest oxidation state achieved is +7. But for your entrance, you please remember, osmium and ruthenium can attain the highest oxidation state of +8. Okay? So I'm going to write now, yeah. Element, you need not write it. Okay? I'm going to write down here. Outer electronic configuration. Okay? And here I'm going to represent it. Okay? So I write now here orbital distribution of electrons and oxidation states. Okay? But I don't know how from I can write. This is the one. No? So I think little portion may go missing. If it is missing, no, please let me know. So it is first is scandium. Okay. Anyway, this atomic number. Okay. So this is 21, and this scandium. I'm writing argon. After argon only it starts. So I'll write, though I'm supposed to write here 4s1, 4s2, 3d1, but I'll go for 3, 4 like that. So it is 3d1, 4s2. So I do not know how I'll be able to write it. Okay. And this is 3d and this is 4s. See, the most stable oxidation state, so I should not say most stable, sorry, I'm very sorry. The more frequent oxidation state or common oxidation state of 3D series is +2. Common oxidation state is +2. Okay, see, 3d1, 4s2. Why it is 4s2? Because these two electron goes out. But it's very interesting here. You'll find that scandium never shows +1 oxidation state. Never. Why? Because after the loss of these two electrons, it has 3d1. So it is one short of the inert gas configuration. So, see, many oxidation compounds in their specific oxidation state, they may not be stable in solid state. That is, you can isolate. But many are found to be stable in their solution state. Even in solution state also, scandium, you cannot find the presence of +2 oxidation state. So, +3. So, at the very beginning, we started with a group oxidation state, which has flouted the information which I have given you, +2. All right. Now, 22 is titanium. 3d2, 4s2. This is this. Okay. Now, it shows the oxidation state of +2. It is there in solution state. When the thing which I am putting in bracket means they are not that stable. They are there, but they are not that stable. +3 and +4. I cannot write it here. Okay. Then 23. Vanadium. 3d3, 4s2. Okay, you can write. See. It shows oxidation state of +2, +3, +4, +5. Then 24. Chromium. You know, it shows an exceptional electronic configuration. 3d5 and 4s1. And you know very well why it is, because to attain extra stability, it borrows an electron from 4s. But why it can borrow? Because the gap between energy gap between these two is very, very narrow, very small. So this, and this. See, in this case, it is supposed to show you +1 oxidation state if it goes out, because this is the valence shell. Why they are showing +2? Because this is the valence shell. Electron is supposed to first go from valence shell. +1. But again, its existence, you can never isolate them in solid state. So, +2, +3, +4, +5, +6. Then, (3d5), 4s2 is the normal ground state electronic configuration. Okay. If you can understand this one, it means half of the chemistry you have learned. It shows highly stable oxidation state of +2. Most of the manganese salt that you are getting is in +2. plus 3, plus 4, plus 5, plus 6, plus 7. See, in case of chromium, plus 5 also is not that stable. And in case of manganese, plus 3 is also not stable. Yes, you can prepare. I have prepared manganese triacetic, but it is highly unstable. So, moment you prepare, you have to use it. And it's a very strong oxidizing. 26 iron. 3d6 4s2. See, this is 4s2 and 6. First, it will go for 1, 1, 1, 1, 1, 1. Then the 6th electron will come here. Now, you'll find very interesting. Going up to 7, suddenly it drop. Very rare. Hardly you can get it in this form. I should have written it here first. Then, okay. See, this is 18. Please remember how to remember. This is 18. How to remember electronic configuration? This is 18. After that, it goes to 4s. So 18 plus 2, 20. 27. The 7 will come here. So 1, 2, 3, 4, 5, 6, 7. Please always remember 18 plus 2, 20. Then 6 will go to the d orbital. 1, 2, 3, 4, 5, 6. Cobalt shows an oxidation state of plus 2 and plus 3. Okay? You'll find in your textbook this is given plus 4, but it's very rare. '28 nickel. So it is AR. Sorry. 3D, I'll write 3D, 18, 20, 18 plus 20, and here will be 8. 1, 2, 3, 4. Okay, this. So 18 plus 2, 20, then 8. 1, 2, 3, 4, 5, 6, 7, 8. So plus 2, plus 3. Okay, and this is also very rare. You can't say it does not form, it is there. Then comes copper. Now you know it again does not follow our normal pattern, because just for atom stability, it actually should be 9. It takes 1 electron from here, so it is 1 and 10. 1, 2, 3. So 18 plus 2. Oh, sorry. No, it will not be like this. Here we have to put 10 electron here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it becomes 18 plus 10, 28 plus 1, 29. So here also it is plus 1 if it goes out. Potential. Plus 2 and very rare, hardly you will get plus 3. I would not have written, but it is given in no books because of the RAM. Zinc. Air 80. 4s2 20. 10, yeah, 30. $20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It only shows plus 2. But thing which I'm not going to wrap is this oxidation state. I told you they show various oxidation state. And here is very interesting. See here. See here. It is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. And the group in which they are going to belong. Group. See here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Don't write. This portion you don't have to write. Okay. Or in the table, if you wish, you can write on the right hand side. Group. Here you can write group. See here. What is our observation? First observation is that common stable oxidation state is plus 2. Except this, all of them show plus 2. Second, oxidation see here. Highest oxidation state increases up to group 7, there is manganese. Then suddenly I cannot write big. See, I'm telling you. Highest oxidation states increases up to group 7, manganese. Then suddenly drops. See here. A drop is there. And very interesting, you see. The highest oxidation state of first series of D block elements matches with the group number up to many. See there, highest is 3, group is also 3, 4, 4, 5, 5, 6, 6, 7, 7. So it's a beautiful relationship is there. After that, it drops. Okay. Now we are going to discuss these two are the observations. Then I'll tell you. Third, the oxidation states differ by 1. See here, 2, 3, 4, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So they differ by 1. But you'll see, remember, just now we have finished P block. In P block, oxidation state differ by 2. So I'll just write here now. I'll change it. Oxidation states of D block elements differ by 1. I'll write within bracket. While in case of P block elements, it differs by 2. Remember, dear, in group 15 we have done. What are the oxidation state it showed? Group 15, 3 and 5. When you go to group 16, oxidation state differ by what? Is either -2, 0 if it's uncombined state, +2, +4, +6. When you go to halogen, it differs by what? Halogen shows either +1, -1, or +1, +3, +5, +7. This is extremely important for your exam. They may ask you, how do D block and P block elements differ? So what you are going to write? You'll write in P block elements, the last electron goes to outermost shell p orbital. It goes to N. While in D block, it goes to penultimate orbital, N-1. And second difference is, in D block elements, oxidation states differ by 1, while in case of P block elements, it differs by 2. Third, all D block elements are metals, while in case of P block elements, most of them are non-metals. Remember this one. Everything I cannot write for you. Okay, so these are the 3 observations that we have made. Now we have written so many. Will all of them be stable? No, all of them are not stable. So which one of them is stable? And it is why. Have you finished writing this one?
Yes, sir.
So please write that. Just I told you, no. Please write down this question. Put inside a box and write. what are the difference between p block and d block elements? What are the difference between p block and d block elements? These elements differ from each other with the following with the following points.
Sir.
Then write 1. In case of p block elements, in case of p block elements, comma, the last electron enters valence shell p orbital. Valence shell, within bracket you write small n. Valence shell, within bracket you write small n. Elements. Sorry, valence shell within bracket, then write p orbitals. While for d block elements, it goes to penultimate, one word, penultimate. Within bracket you write n minus 1. D orbitals. Written?
Yes, sir.
Then write second. Then write this one. You already written now? The oxidation stage of d block elements differ by 1. Then you remove the bracket and write. While in case of p block elements, it differs by 2. It differs by 2. Sorry.
Done, sir.
Okay. Then third, I told you to write down. All d block elements are metals, while most of the elements of p block elements, most of the p block elements are non-metals.
Yes, sir.
Now, I'm going to tell you that which oxidation state will be stable and why. So write. I'm going to not remove this one because I'm going to show you here. Factors controlling the stability of oxidation states. Okay, so I'm going to now mention here A. Stable oxidation, sorry, stable electronic configuration. See, first you hear, then you write. What is the meaning of stable electron configuration? There are three types of electron configuration which are stable. One is noble gas. Noble gas means what? It will stop up to air. After air is the noble gas. Then after that, if all the electron goes out from their d and s orbital, then it has attained noble gas configuration, or what I can say, we call it D0. Okay. Put it down here. D0 or noble gas configuration means after D, after the air, all orbitals have become empty. Now, see here. Scandium has 3 electrons. Scandium has 3d air. 3d1 over s2. If I write here -3, it will become what? 3d0 over s0. Then what is left out? This, is it not d0 configuration? Huh? So, similarly for titanium has, I told you how to remember, titanium is 22. So 18, then 2 goes to s orbital 20, 2 goes to d. If you remove 4 electron, what you get? You get here +4 oxidation. See here. So what are the examples here? Example is scandium. I'll write here now. +3. Titanium +4. Vanadium +6. Chromium +5. Vanadium +5. Chromium +6 and manganese +7. So why they are stable? Because they have attained D0 or noble gas configuration. All right. Very good. Then from here, what we have learned? See, suppose I have taken here, they may give you how titanium 3 plus is going to behave. See, titanium 3 plus is one short of D0 electronic configuration. What is going to happen now? If we lose one electron, does it not attain more stable electron configuration? See, you have made titanium +3 oxidation state compound. But titanium is looking that if somehow if I can lose one electron, then I will going to attain more stable electronic configuration. Okay. So in that case, what you want to what will be the nature of this one? See, any element, any ion, any compound, when it gives electron, it is a strong reducing agent. Please remember, what will be the nature of these compounds? They will be acting as a strong reducing agent, because reducing agent shed or lose electron and give it to others. So what is going to happen now? They'll undergo reduction. See. So if you have taken now vanadium plus 4, vanadium plus 4 is immediately going to give you, become plus 5. So this also will be a reducing agent. Please remember, vanadium pentoxide is an oxidizing agent, strong oxidizing agent, but vanadium plus 4 is a reducing agent. Why vanadium pentoxide is a strong oxidizing agent? Because from plus 5 it comes down to plus 2. There is a separate story that we are going to discuss separate. Okay? See, why did I put plus 5 inside bracket? I have put plus 5 inside bracket because moment we form plus 5, it loses 1 electron, goes to plus 6. Or it will come down to plus 3. Okay. Then what are the other types of stable electron configuration we can have? We can have half filled, or we can go for completely filled. So second is what? I'll write here D5 or half filled. Half filled configuration. So where you can go for half filled? See here. Let us come to this one. See, manganese has how many electrons? Manganese is Ar is 27. Manganese is 27. 27. So it is 18. 3D 4s2. So it is plus 2. So how much have to add here? Manganese is 26. 25. Sorry, dear. 25. So it is 5. So I'll write 5. From here, if I subtract 2 electrons, which one will go? This one will go. So what you are going to get here? Ar 3d5 4s0. Is it not half filled? Is half. Okay. Now let me go for iron. Ar 18 3d5, sorry, 3d6 and 4s2. Okay. From there I remove 2 electrons because I have written, see here iron. So what do I get here? Ar 3d6 40. See, is it not one extra to that of half filled? So is immediately going to lose 1 more electron there. So what you are going to get now here is so 2 plus. So Fe 3 plus. What is this electronic configuration? Ar. It is 3d5. See, suppose you have taken ferrous chloride or you have prepared ferrous sulfate, make a solution and keep it overnight, you will find it will be converted to ferric sulfate or ferric chloride. Why? Because this is more stable than this. All right. So the extra stability of example, the extra stability of manganese plus 2 and iron plus 3 is only because of more stable half filled configuration. But see, very interesting thing. Here I have written +7 is more stable, and here I have written +2. So between these two, which is more stable? See, this is more stable than this. Remember, we have done redox reaction. I don't know whether you have still remember. Okay, we have written here now 8H plus 5 electron. It gives us Mn2 plus 2 and 4H2. See, the reaction moves from left to right. It does not move from right to left. Why? Because this is more stable than this, and we have understood its weakness. And because of that, permanganate is being used as an oxidizing agent. See, oxidizing agent helps other to lose electron and itself gain it. See, by knowing their stability, we can use them for our own purpose. Okay, so we find that energetically, manganese 2 plus is more stable than manganese 7 plus. See. Now what we have now? D10 configuration, D10 or completely filled configuration. So that you can make it out here. Zinc. See, zinc is having an electronic configuration of Ar 3d10 4s2. So the 2 electrons from the s orbital goes out. Then it gives you d10 configuration. From here, copper, it is 3d10 4s1. When this electron goes out, then we get 3d10. So which are the ions shows complete configuration? Copper +1 and zinc +2. So it is copper +1 and zinc +2. So now, out of so many oxidation states, we could justify the stability of this oxidation state on the basis of electronic configuration. You should know, because you are intelligent enough. See, to me, it's not a matter of question of science, arts, and commerce. It's not the question that how much you got in exam. I know a person is intelligent from the day he can tell lie. Okay, if the person is abnormal and he's a small child, he cannot tell lie. When you have learned the art of telling lies and giving excuses, then you should know you are bright. So just to test your brightness, don't go on telling lies every day. Huh? Understood now?
Yes, sir.
Very
Yes, sir.
good. Now see, most of the reactions here we carry out in aqueous medium. So all the ions which are forming, they are staying in water. Okay. So in water, what happens? How do the water accommodate them? Water accommodate the ions in forming this type of cavity. Okay, cavity that there. So there is a specific shape is there. If any ion fits there, it is dissolved. If it does not fit, it will precipitate. Okay, so we call that one hydration enthalpy. So now second factor is the hydration enthalpy. B. Because hydration enthalpy, if you can accommodate it very nicely, then ions become extremely stable and they release a huge amount of energy. Hydration enthalpy. See here. In hydration enthalpy, let us take copper 1 and copper 2. Copper plus 1, cuprous. And copper plus 2. See, it is D10 and this is D9. See, to remove one electron from very stable D10 is very, very difficult. Extremely difficult. But it's very interesting. If you have taken, see, copper 1 compounds, copper 1, say it is cuprous chloride, cuprous bromide. You know, dear, none of them are soluble in water. Why? Because you know, more the positive charge, more is the effective nuclear charge. And more the effective nuclear charge, smaller is the ion. So the size of the copper 2 ions are smaller than copper 1. Okay? So you have taken copper 1, cuprous chloride is a white insoluble precipitate. Leave it for 1 day, you'll find half of the precipitate has dissolved and the solution has become green. Why you know? Because copper loses its own electron to get it hydrated. With the size decreases. Who provides the energy? It is the hydration enthalpy. Once it goes, huge amount of energy it releases. So that energy pulls out one electron from the D10. So please remember, copper plus 2 is more stable than copper 1. Okay? So it flouts the stable electronic configuration. Second, we find chromium. See, chromium shows so many oxidation state, +1, +2, +3, +4, +5, +6. So we find that chromium +3 species get immediately solvated in water molecule. So in that case, you will find the chromium +3 oxidation state is the most stable among the series of the chromium that you have. Okay? So in that case, what you will write here? The reason is what? Copper +2 and chromium +3. So I'll give you an example. If I cannot give you an example, don't trust me. See here. Again, this is another redox reaction I am giving you. +7. This is +6. And after the process is over, it gives me +3. So we write it here. We write here now here 14H plus, and it takes 6 electrons to give you 7 molecules of water. See, this is, I told you this is supposed to be stable. Why? Because it is having D0 configuration. And it is, in this case, see here, it is +3. So it does not follow any stable electronic configuration. Neither half filled. See here, half filled is this one. So this is also not stable. This you can isolate in solid condition, but if you leave it in aqueous solution, automatically it will come here. So why chromium 6 compounds are very strong oxidizing agents? Because chromium +3 oxidation state is highly stable in aqueous solution because of due to large negative hydration enthalpy. याद रखना. C, it will be a little difficult for you to understand. We call it large crystal field splitting energy. Have you done quotation chemistry? Quotation chemistry is done in a school.
Oh, Mama.
Oh, yes. So then, no, because you are my Bhanji, so you are supposed to know. She knows everything by birth. Okay, then. Any other species? Hey, Ponsan. Quotation chemistry done. Forms
No, sir.
most of the cobalt salts have +2 oxidation state. But when it forms complex, it +3 oxidation state. So this one you please leave it now. When we will go to quotation chemistry, I'll tell you. So higher the oxidation state, more is the crystal field splitting energy. So in that case, cobalt 3 complex cobalt attains +3 oxidation state in complexes because it has higher crystal field splitting energy. So I'll write down here. Cobalt exhibits +3 oxidation states in their complexes as they have higher crystal field splitting energy. If you can convert again this complex into a normal salt, again we will come down to +2. Achana of D. This we call it thermodynamic stability. Okay, you'll find that does not exist in this group. It is the 3D series. If you go to 4D series, exactly below nickel you will have platinum. So we'll find that nickel +2 compounds are more stable than platinum +2. But if you have gone for nickel +4, they are less stable than platinum. This I have told you only for your entrance exam. Why you know? To lose 2 electron, nickel has to utilize first ionization enthalpy and second ionization enthalpy. So when you add first ionization enthalpy and second ionization enthalpy of nickel, we find it is less than platinum. Okay, ionization enthalpy, if you add it, it is less than platinum. So nickel will easily form +2. But if you go for platinum often forms +4 oxidation state compounds, because if you add first, second, third, and fourth, ionization enthalpy of platinum is much lesser than nickel. So I told you all the reasons for which the stability of oxidation states. And at the beginning I told you that when I was discussing with the ionization enthalpy, I told you I cannot explain many things. So why did I tell you? See, the species which is more stable, suppose I have gone for +2. If I compare this +2 and this +2, you will find iron automatically goes to +3. because that is more stable. So here he spends very small amount of energy, so its ionization enthalpy is less. When you go to +2 to +3, until unless you don't form complex, cobalt will never go to +3. Okay, so you will be asked about to interpret the behavior of this compound. Suppose you have taken, they have given you what is the nature of manganese +3 complex compounds. See, this is more stable. Why? D5, half filled. So in this case, if you have made +3, will it not immediately like to come here? So how to come from here to here? It positive oxidation state decreases only when you add electron to them. So in that case, Mn+3 will be very strong oxidizing agent. But if you have gone to ferrous, ferrous is not stable, it wants to go to +3. How it can go to +3? Only by the loss of electron. So please remember, ferrous salts are very strong reducing agents. So this is the way the question will come. So you should have little bit idea and what are the factors are present there. Clear? Huh? So I told you, these are in your note, you'll find everything I have written down. So because of that, I told you, try to understand and write less. Okay. See you tomorrow. Good night.
Thank you, sir. Good night, sir.
Good night.